Hello and welcome to VEX Robotics for Competition, a tutorial for new teams, presented by McCallum Robotics of Austin, Texas, Team 8756. This tutorial will cover programming for three more typical competition sensors: the optical shaft encoder, the integrated encoder back, and the gyroscope. We'll first look at the optical shaft encoder. You can see here I've just mounted a single encoder on the outside of the left rail, and it's wired to ports 3 and 4. Let's go to the online wiki, Cortex, Sensors Overview, and it is a digital sensor that we already set up, and they call it a quadrature encoder here. And we're here looking to see what units it uses. And unfortunately, it doesn't actually say on this particular example. So it tells you that it divides the rotation into like counts, but it doesn't say how many. But if you look down here, you can suss it out. It says 1800 is 5 rotations. There's 360 counts or ticks per rotation of the quadrature. For a little bit more information, I can look at the optical shaft encoder page at the VEX Robotics wiki, and it describes a little bit about how it works. And then it also has a formula here for how you calculate the distance. Basically, the circumference times the number of rotations is how far it will go. So let's go back to our program. So we'll describe what we want, which is a function to run AutoDrive for a specified distance, and we'll have it called AutoDrive distance, and we'll take two variables, speed and distance, and we'll use distance in whatever units we want to use. If this is an American robot, it'll be inches. So the quadrature encoder is a lot less finicky than the potentiometer. You can in fact reset it whenever you want. So at the beginning of this void function, we'll reset it to 0, so that from then on it'll count from there at 0. And then we'll need to define how many ticks of the quadrature encoder relate to distance. So we need to convert the distance into ticks. So our distance, we're giving it in 20 inches. The diameter of the wheel times pi is times the number of ticks is how many ticks is in that distance. So this converts that. So then we also need to have a while loop. So we're checking for while the absolute value of the quadrature left is less than the ticks. So we've determined that we need a certain number of ticks to go the distance we want, and while this is less than that number of ticks. This could be a negative number, and that's fine. It really doesn't matter which way it is, because the absolute value is just the number without a sign. And while it's at that, while it's less than the number of ticks, we are telling it to drive at the speed we set. So we only need one more bit, which is to stop it once it reaches the ticks. And there you go. That is the basic function. We can test this and see how it does. The function reads void AutoDrive test, take an input of speed, so how fast you want it to go, and distance, which is in the units you want, we're saying inches, and we'll tell it a number of inches, it converts it to ticks, runs until it reaches that number of ticks at AutoDrive speed, and then stops. I've written the short autonomous down at the bottom, and the autonomous is this: it lifts the arm so that it doesn't drag on the ground, and that it drives at 80, so forward, for 20 inches, waits a second, and it records a value so we know what the reading was when it was done, and then it backs up the same amount, records, runs forward, records, runs backward, records. So we can see how it did visually by watching it on the camera, and then we can assess how it did by looking at the actual quadrature readings when it finished the task. The orange tape is marking the 20-inch distance we are aiming for. Looking at the debug window, the number of ticks we should be seeing is 572. So both the video and the data we're getting show that we're going way too far. So what we're seeing is the effects momentum. When we did our auto arm height, we saw that we had to account for momentum for the arm. The robot has more mass in the arm, and it's moving faster, and so we actually have more of an issue with momentum when we're dealing with drive functions. So we'll need to add something that slows the drive as it reaches the end, as it reaches the number of ticks that we want, and then stops it. So if we want it to slow and then stop, we can say that go absolute sensor value, quad left, until you reach 60% of the ticks, so that's full speed, And then we'll have a second while loop once that's done to complete the run to the ticks, but at 1/3 speed. Then we'll have a small reverse and then shut the motors off. I'm also looking here at this math we're doing to set the number of ticks, and I would like to make this more universal. Right now it's for only 4-inch wheels and only quadrature. We're going to be doing the integrated encoders next, and they have a different value for this. So I'm going to set some globals. So here we have the globals. They're up at the header, and we're going to make one called wheel diameter, and we'll set it to 4 because we'll be using inches. And we'll have another one called encoder ticks, and we'll set it to 360. You'll see in my comments I can say if you want to do centimeters for your wheels, you'd reset that variable to be a float at 10.16, and then whenever you gave distance values you could give them in centimeters, and the formula would work. And then also for encoder ticks, it's at 360, which is what the optical shaft encoder wants. And later on we'll be changing that number to match our integrated encoder backs. When we replace the formula for ticks, it will look like this. Instead of the 4 we have wheel diameter, and instead of the 360 we have encoder ticks. It'll be the same value because we set them in globals. I'll now test it and see if we get better results. So you can see from both the video and the data that we're capturing that the results are much better, although it does go slightly past the 572 that we're aiming for. In the end, the best way to get an accurate result is to go as slow as possible. I'll show that by running the same autonomous where we're going 80 for the first 2 passes and 60 for the second 2 passes, and see that we get cleaner results. So you can see that you do get better accuracy the slower you go. However, there is some point at which if you go slow enough, the bot will not actually drive forward, and therefore the encoder tick will never be met. So you have to accept that sensors, although much better than time-based programming, are not perfect. The integrated encoder module is an optical shaft encoder that's in a form that just replaces the back of an existing motor. And I've mounted 2 on the bot, one on motor 2, and you can see that in the picture, and another on motor 3. This gives me an encoder for both the left side and the right. If you go to the main page of the RobotC Online Help Wiki, there is a link in the bottom right that goes to programming for the VEX integrated encoder modules. And it gives you some good background information about it. They're slightly different than the other sensors because they use the I2C port, and that port is daisy chained. So you plug the first motor into it, and that becomes motor 1 on that sensor chain. And then you plug the second motor into the first, and the third into the second, and so on. And so this would be the first, second, third, and fourth, and you could have up to 8. Also on that page we find the conversion factors. 2 our 393s are 627.2 counts per revolution when it's high torque, or otherwise 100 RPM, and 392 counts per revolution when it's in its 160 RPM gearing. The base code for the integrated encoder modules is basically the same. Here's where we left our optical shaft encoder code, and integrated encoder module code looks like this. So what I've had to do is just replace the reference to the sensor value for quad left with this nomenclature, which is how you access the values of the left and right encoder modules. I also had to update the eDrive ticks global variable to the current value, which is up here in my globals. So the number of ticks per revolution is what we're defining. It was 360, and now it's 627 because our motors turn at 100 RPM. So this is the code, and we had to clear 2 encoder modules because there are 2. And if we left it like this, we really wouldn't be getting the advantage that we have from having two. You may have noticed in the videos while the bot was driving back and forth, it tended to turn just a little bit. The motors don't always operate at exactly the same speed. So just out of the box, some motors will turn a little bit faster than others, and more often than not, one side of your bot will go a little bit faster than the other when given the exact same motor values. So we need to add a little bit more code, which would look like this. So let me walk you through that. We cannot simply do an auto drive anymore because we want to tell the left side and the right side to do different things. The concept when you're pairing up two different encoders is that you want to consider one side, and in our case the left side, to be the standard, and then the other side you want to match to it. So you check both sides, and in this case we're taking a variable called RDiff, and it is looking at the absolute value of the left encoder and subtracting the absolute value of the right encoder. So now we know the difference between the two sides. And what I want to do is if the right side is behind, going slower than the left side, I want to give it a little bit more motor power. And if the right side is ahead of or going faster than the left side, I want to give it a little bit less motor power. So here's another integer I'm setting called rmod, and it's sine r difference. And sine r difference is just taking the sine of it. It's a C function. And I'm multiplying that by speed and multiplying it by 0.1 or 10%. So I'm basically saying if the right side is going too fast, this will make it go slower by 10%. And if the right side's going too slow, it will make it faster by 10%. And then I need to give motor commands to each motor separately so they're getting the correct speed. And otherwise it's the same function. 60% of the time it goes full speed, the last 40% of the time it goes 1/3 speed, and then it has a little stop at the end. So I have the same autonomous code down at the bottom, and we can test it and see how well it does. See, now the camera has a bit of a fisheye, so it might be hard to tell that it's driving straighter, but it truly is. And looking at the coder values in the debugging window, with the target is 1000, and you can see it's hitting it very closely. Another thing that we can do now that we have two encoders, one on each side of the bot, is we can use the encoders to create a turn function. So we want to create a function to turn the robot a specified number of degrees at a specified speed. The function that we want to write we'll call AutoTurnEncoder to distinguish it from our turn time, and it'll take two variables, speed and degrees. It will start similarly to our encoder drive function, where we clear the encoders and we set the number of ticks equal to a value that we can use to evaluate in a while statement. However, there is no intrinsic number of ticks it takes for the robot to turn a number of degrees with the sensors. The geometry of your robot is going to determine how that works. So what we'll need to do is we'll need to iterate through multiple tests to evaluate how many ticks it takes this particular robot to turn. And so what I've done is I've commented out the line where we calculate the ticks based on the degrees, and the constant we'll be setting in a minute, and I've altered the variable names up in the function call so that ticks is here where degrees was. That way we can send it ticks directly in Autonomous, and we can test it multiple times. What we want to do is assess how many ticks does it take to turn 90 degrees. That's a great test point. You could do it any value, but 90 is easy to measure, and it's a pretty broad angle, so it's a pretty good test. So I did a good bit of testing, and I found out that it takes about 590 ticks to turn 90 degrees on my build. And if I do the math on that, I create this constant that I want to have, and it's a float because it's a decimal number, and I don't mind using floats. And I'm calling it e-turn ticks, and it's 6.56 e-turn ticks for 1 degree of rotation on my bot. And this can be calculated with the test and check that I just recommended. You could also break out your trig and figure out how many degrees it should turn based on that. So now I'm ready to write my real turn encoder void. And what I want to do is make it look basically like my drive straight encoder. So here's what it looks like. It's got all the same parts. I'm clearing the encoders. I'm creating a conversion that makes my ticks equal to the degrees I'm sending it. And then I'm testing that with the left encoder. And I'm checking for a difference and modifying my right motor speed. The difference with this check is that I need to subtract the mod in the turn function because you know the right side is going the opposite of the left. I did it a little bit different where I send it a slower speed of only 80% of the speed because when you're turning, you're going to give it slower drive speeds generally. 60 would be plenty of drive speed, and you might go less than that. And if I tell it to go a third of the drive speed and I'm initially starting with a 50 or 40 or 60, then it may not even be able to turn. Otherwise, basically the same, and I'm ready to download. The autonomous function I'll use to demonstrate the encoder turn is very similar to the drive straight. I turn at 60 motor speed, 90 degrees, wait a second, record the value, and then keep turning. So it should turn a full circle by the time it's done. If this looks just a bit too easy, be aware I did spend a couple hours tweaking this to get it to turn just the way I wanted it to. And it turns pretty well. Our goal is 590 for 90 degrees, and it hits that pretty darn good each time. The final sensor we'll be looking at is the gyroscope. It's a very small sensor, and the key point is that it must be installed horizontally, and you want to install it as close to the center of rotation as you can. The sensor overview in RobotC Online Help Wiki shows that the gyro is an analog sensor. It returns values in tenths of degrees, and so one full rotation would be 3600 degrees. So it goes from 0 to 3600 turning counterclockwise and 0 to negative 3600 turning clockwise. Somewhat counterintuitive, but that's the way it works. There's a great blog post that covers how the sensor works, so you can access it from here. The gyro is actually very straightforward to use. So we want to make a new turn function. It's going to be a function to turn the robot a specified number of degrees at a specified speed. So we'll create a function called AutoTurnGyro, and it'll take speed and degrees. The function itself is going to look really similar to what we've been doing. We clear the sensor, we convert degrees to ticks, and all it takes in this is to multiply it by 10. We could actually give it degrees 10 by giving it 900 when we want it to go 90 degrees, for example. But I feel it's easier to just do this calculation. We're testing the absolute value of the gyro, so it doesn't really matter which direction we're turning. We're starting slow for the first 60%. I've added 2 stages of slowing. This is such a sensitive device. It's a tenth of a degree. And so to actually catch it right at the ticks, you got to ease up onto it. So we start out at 60%, then we go at 80% for the last little bit, and then we slow down to just 40% and give our stop. The gyro does have recommended clearing on it. It can have a value stored on it, and it can get jostled while you're moving your robot around onto the field. So it's recommended that in pre-autonomous you clear out the sensor, and the best way to truly clear it out is to set the sensor that you're calling gyro to none, which basically says it doesn't exist anymore. Wait a little bit, set it back to gyro. It takes 1.1 seconds for it to recalibrate the gyro. So if you give it 1.5 seconds, you're good. And then it'll have a clear 0, and it's ready to give you good values when you run it in autonomous. The autonomous I set up is very similar to the encoder auto turn that I ran. It turns 90 degrees positive 60 speed, but then it turns negative 60 speed, positive, negative, records a value each time for analysis. I ended up lowering the drive speed to 55 down from 60. And you can see the results are super consistent. If you look at the debug window, you can see a previous test being replaced with this test, and you'll see that it's super consistent among itself and very consistent test to test. It still goes slightly too far, but if I try to slow the motor down anymore, it just stalls and can't quite make the turn. That covers all the sensors typically used in competition. There are others available, such as an ultrasonic sensor line trackers, light sensors, but they're not very good in dynamic situations when there's objects moving beyond your control, and therefore they're not covered here because they just really don't do well on the competition field. Thank you for watching.